All right, the citric acid cycle. This is where the magic happens, as we explained last time. For every molecule of glucose, we end up with 2 molecules of acetyl-CoA, and this is the overall yield from those two GTPs, 2 FADHs, 6 NADHs. We will see soon that NADH and FADH can go to the electron transport chain, where they are worth NADH 2.5 molecules of ATP per molecule of NADH. And then, of course, from FADH, we get 1.5 molecules of ATP per molecule of FADH2. So, as I think we totaled up 32 molecules of ATP from glucose, and of those, about 20 of them, I think we did the math right, yeah, 20 of them come from the citric acid cycle. So this is a big deal because most of your energy, that means, comes from this. So I want you to keep a couple of goals in mind with the citric acid cycle. Goal number 1 is loss of CO2. And there are 2 ways we know of how to lose CO2. The first is what I've called before spontaneous, meaning happens just because, spontaneous decarboxylation. And this happens whenever you have a specific functional group. Do you guys remember what it is? It's called a beta keto carboxylate. And the key feature of the beta keto carboxylate, just to draw a simple one, is that you have carbonyl carbon in the carboxylate, you have the carbonyl oxygen that is the kicker-offer, and then here you have an enolate leaving group, such that you can break the bond between the carbonyl carbon and the alpha carbon to get a resonance stabilized enolate. We've seen that, I've showed you that before, originally in the mechanism handout, and we talked about it when a little bit when we were talking about the pyruvate dehydrogenase complex. So one key target functional group, if we want to lose CO2, is we're going to be anxious to make a beta keto carboxylate. And then the other option we have for loss of CO2 is something similar to what we saw when we decarboxylated pyruvate. We called it oxidative decarboxylation of an alpha keto acid. And the example of that was pyruvate. And the point was that in order to get this to happen, the carboxylate oxygen can't be a good kicker-offer, because what's here is not a good leaving group until you involve TPP, lipoamide, and NAD+. So that's our other potential target molecule, is an alpha keto acid. We can use enzymatic machinery similar to the pyruvate dehydrogenase complex, and we went through that mechanism last time. It's pretty difficult. But those are our 2 target arrangements of atoms that allow us to lose CO2. So that's our first goal in the citric acid cycle. I don't have enough room to write stuff. That's like messy and yuck. So maybe we'll just go here. Paste. Better-ish. That's still messy, but it's less distracting. Okay, two different options, two different key functional groups. So as we talk about the reaction, and before we do the mechanisms, we're going to sort of overview what happens. And I want you to pay attention to how nature gets us to those two key functional groups. So that's goal number one. Once we've done that, goal number two is going to be to regenerate the oxaloacetate starting material and along the way, our goal is to make as much NADH, FADH2, and GTP as possible. So that's really, those are the two overarching goals of the process. And just like I tried to show you in glycolysis, the early steps of glycolysis were all about getting the ketone in the right place so you could buy a retroaldol reaction, divide fructose 1,6-bisphosphate into 2 3-carbon pieces. Similarly with the citric acid cycle, if you keep these goals in mind, you'll start to appreciate the chemical logic behind what's going on here. Trying to memorize what is possible, it takes a lot of energy, but if you're able to organize it and get a sense for what nature is trying to do and see how it makes sense chemically, that'll help. Okay, so let's just overview. We start with acetyl-CoA, and I've starred the 2 carbons in acetyl-CoA. Those come from glucose. And we're going to follow their fate through the citric acid cycle until we lose track of them. There will come a particular point at which we lose track of them totally. But for now, let's just highlight the molecules from glucose. I don't know, blue for, no, just one color is probably sufficient. Okay? So we start with acetyl-CoA, and then the other reactive partner is oxaloacetate. Oxaloacetate is a 4-carbon diacid with a ketone on carbon 2. Now, if you were looking at oxaloacetate, and if I told you that oxaloacetate is going to be an electrophile, which functional group would you worry about? Which functional group would you focus on? Carboxylate, or ketone? Which one is the most reactive? Ketone is level 1, right? Carboxylates are level 4, so we can ignore them. I think I want to use purple for acetyl-CoA. Just changing my mind on colors. So let's highlight the blue carbonyl carbon of the ketone, and the pink, let's highlight in pink the carbonyl oxygen like we've done so many times. What is the LUMO of a ketone? Yep, it's the carbon oxygen pi star. So a nucleophile must attack at the carbonyl carbon wherever this arrow starts, and then we must break the carbon oxygen pi bond. So we ought to expect that, just knowing this is a ketone without knowing anything else, right? Okay. The acetyl-CoA is going to be a nucleophile when we first do a proton transfer to make it an enolate. So in this reaction, we're going to have to remove a proton that's alpha to the carbonyl carbon, make an enolate, and then that enolate's going to attack the carbonyl carbon. That is going to generate an intermediate that I will draw for you here. We'll worry about the mechanism of this later. I mostly want to just talk through it in words now. Here is the blue ketone carbonyl carbon. Here is the oxygen that, when this pi bond breaks, becomes negatively charged, and then it picks up a proton. Here is the new bond that is made And then here is the alpha carbon and the carbonyl carbon of acetyl-CoA. So those two carbons end up here. This intermediate, which was not shown, is called citryl-CoA. And you'll notice if you compare citryl-CoA to the product, we've gone from a thioester to what kind of functional group here? Carboxylate. Thioester is what level? Nope, esters are 2, thioesters are 1. Because the SR minus leaving group is a much better leaving group than an OR minus. Who spells level L-E-V-I-L? Leville. Yeah, I'm just gonna leave it there. Level 1 to level 4. Okay. So what's happening here is that the thioester now, the coenzyme A thiol, is acting as a leaving group, and water is acting as a nucleophile. What is the LUMO of a thioester? Yeah, I hear some of you saying it, carbon, oxygen, pi star. So again, when a nucleophile attacks, we expect to see this kind of thing going on. Attack the pi bond, attack the pi star, break the pi bond, electrons go out onto the oxygen. Who can describe for me in words what you expect to happen going from the thioester to the carboxylate, water acting as the nucleophile? What do you think has to happen? Deprotonate water, then oxygen attacks what? Carbonyl carbon at the pi star, then we break what? The pi bond. Then what? Then we get a tetrahedral intermediate. Something gets kicked off. What gets kicked off? Coenzyme A thiol leaving group, and then that deprotonates the resulting carboxylic acid to get you this intermediate called citrate. Okay, we'll go through and draw that. In fact, that's the first question on your quiz, but I think it's helpful to have an overview before you start. We'll do that in a little bit before you start worrying too much about what the arrow pushing is. Okay, so step 1 of the reaction for the citric acid cycle is actually 2 reactions. First, the reaction of an enolate with a ketone is called an aldol reaction. You've done a retroaldol reaction before. This is an aldol in the forward direction. You can tell that we've made an aldol product because starting with the thioester carbonyl carbon, there's an OH at the beta carbon, and beta hydroxy carbonyl compounds are aldol products. So this involves an aldol reaction in the forward direction, reaction of an enolate nucleophile with a ketone electrophile to give a beta hydroxy carbonyl compound. Then the second reaction catalyzed by this enzyme is, we would just call that thioester hydrolysis. And the thioester hydrolysis happens via deprotonation, addition, elimination type mechanism. Okay, so remembering our 2 main goals, loss of CO2, but our first goal is the one we're going to achieve first. That's why it's our first goal. In order to lose CO2, we need to have a beta keto as carboxylate or a beta or an alpha keto carboxylate. Tell me about citrate. Is that oxygen beta to anything? Is it alpha to anything? So it's beta to that carboxylate. It's also beta to that carboxylate. And I need another color. Oh, fine, we'll go blue. It is alpha to the other one. So we've kind of got an oxygen that's at least in the right place relative to those carboxylates. What's the problem with that oxygen? Why doesn't it, what's missing if we're trying to get a beta keto carboxylate or an alpha keto carboxylate? Not a ketone, right? Let's talk briefly about how nature oxidizes alcohols to ketones. I think you've seen this before, but my guess is you haven't quite put all the details together. So we'll just call this biological oxidation of secondary alcohols to ketones. So a secondary alcohol is one where the OH is attached to a carbon that's also bonded to two other carbons. So a secondary alcohol, that's what this symbol means, secondary. Secondary alcohol means a carbon that's bonded to two other carbons and then an OH and then a hydrogen. Oxidation of secondary alcohols gives ketones, and in a biological sense, what happens is you use NAD plus as the hydride acceptor or the hydride catcher, and then you use some base associated with an enzyme to deprotonate the OH group. This oxygen then acts as a kicker-offer. Electrons kick down to form the ketone pi bond, and hydride leaves with its electrons and is caught or received by NAD+. And that gives you your ketone, and the hydride, meaning the proton, the green proton, and the electrons in its carbon-hydrogen bond end up on what's called now NADH. Okay? You have to have a CH bond for that kind of thing to occur. By the way, make a prediction. If we do this same thing, I won't draw the mechanism, but if we do this same thing with a primary alcohol, what is the product going to be? Yeah, it would be an aldehyde. And the way you can tell that happens is, remember, an enzyme removes the proton on the oxygen. The oxygen then acts as a kicker-offer. This becomes the carbonyl carbon, and one of the hydrogens leaves with its electrons and gets handed off to NAD+. So in order to oxidize an alcohol to a carbonyl, you must have at least one hydride. Okay? What's the problem? Why can't I oxidize a tertiary alcohol? I could remove this proton for sure on the pink oxygen, but I have no hydride leaving group in air quotes to indicate, they're not really air quotes if you write them out. So, okay, no hydrogen leaving group for NAD+ to receive. Okay, so you can't oxidize a tertiary alcohol. With that in mind, any questions about that? That in mind, let's go back and look at citrate and see what situation we're in. The oxygen is in a decent spot, but what kind of alcohol is it? Are there any hydrogens? No. Citrate is a tertiary alcohol, and so it can't be oxidized. Now, that's a big problem because our major goal at this point is to lose CO2. If we could only oxidize that oxygen to the level of a ketone, we could do spontaneous decarboxylation of a beta keto acid, but the OH is on the wrong carbon. So the next two steps are all about moving the OH to the right carbon. And this is kind of cool. We'll talk about how this happens, but the first is a dehydration reaction catalyzed by aconitase. Basically, aconitase removes this proton on the orange alpha carbon. Electrons kick down and OH leaves, getting protonated as it leaves. That's a deprotonation, elimination, and reprotonation reaction called dehydration, because effectively you remove water. So in citrate, loss of water gets converted to this molecule called aconitate. And this is an intermediate, and it's a very, very interesting intermediate because we'll keep the colors blue and orange going. If you look at aconitate, this blue carbonyl carbon has an alpha carbon and a beta carbon. The blue carboxylate is what we would call an alpha beta unsaturated carbonyl compound. And it's been a while, by which I mean probably 8 days or 9 days. I told you that alpha beta unsaturated carbonyl compounds are characteristically electrophilic at the beta carbon. And we talked about how that's a product of resonance. You can draw a resonance structure where you move this pi bond here and then move that pi bond there, and that would leave a positive charge on the beta carbon. Okay, so I'm going to say that the blue carbonyl, because of that alpha beta unsaturated carbonyl compound, the blue carbon here is electrophilic. Okay, meaning a nucleophile could attack there. Similarly, if we look at the orange carboxylate, this is the alpha carbon and this is the beta carbon. So from that perspective, this orange beta carbon could also be electrophilic. Yeah?
For the blue writing, could the beta carbon be on the other side?
Yes, this could be, are you saying, does this also count as a beta carbon? It certainly does, though it doesn't have the double bond between alpha and beta carbons, so it doesn't participate in the reaction. Yep. Good. So you've got in this molecule 2 carbons that can receive nucleophiles. Alpha beta unsaturated carbonyl compounds are electrophilic at the beta carbon. Now, in this reaction, we have just barely lost water. We did a dehydration reaction. In the next step, water is going to come in as a nucleophile and do, instead of a dehydration, it's going to do a hydration reaction. Now, when water left as a leaving group, where did it leave from? From which carbon? Relative to the orange carbonyl carbon, beta, right? But relative to the blue, it left from alpha, right? So if water came back in and attacked blue alpha, orange beta, that would ultimately lead back to citrate. And that happens, and that's why this arrow is reversible. You can go back and forth between citrate and aconitate. But instead, and we won't push the arrows, but we'll talk about it briefly. We're going to do this pushing the arrows later. We're just giving you the overview. If instead water attacked the blue beta carbon and the orange alpha carbon, that would give me the OH there, right? In this reaction, basically, it's the reverse of the elimination reaction. You deprotonate water. Hydroxide acts as a nucleophile, attacks the blue beta carbon. These electrons between blue alpha and beta kick over onto blue alpha, and then we pick up a proton from some acid. Okay? We'll show you that arrow, but that's conceptually how it happens. The product is isocitrate. Same molecular weight as citrate. And what you can't see here is implied but not shown is the hydrogen that gets added in the hydration reaction. What do you notice about isocitrate? What kind of alcohol is that? Secondary, right? It's got, importantly, unlike citrate, isocitrate has an H with its electrons on the secondary carbon. The secondary alcohol of isocitrate can be oxidized.
Can you give us a refresher on what's primary?
Yeah. So a refresher on what's primary, secondary, tertiary for alcohols. A primary alcohol is here. This is an alcohol where the OH is attached to a carbon that the blue carbon is only making one other carbon-carbon bond. So one is primary. If it's two carbon-carbon bonds, that's secondary. And if it's three, that's tertiary. So if we go back to isocitrate versus citrate, you can see that this carbon makes two bonds to carbon and one to hydrogen. In citrate, this one makes three bonds to carbon.
Thank you.
Yep. Others? So the whole point of that dehydration and rehydration is to slide that OH over one carbon. Having done that, you are now ready for oxidation. So if we did an NAD plus mediated oxidation, a base would remove the proton on the alcohol, electrons would kick down, and hydride would be delivered to NAD plus. That would leave what kind of functional group here? Ketone, right? So we're going to draw that intermediate, and it's an intermediate. The enzyme that does this is called isocitrate dehydrogenase. Here is the ketone that we just installed. We just lost the hydride. Now let's see whether that meets our criteria. Carbonyl carbon, orange carbonyl carbon, orange alpha. So yes, in fact, we do have a ketone alpha to a carboxylate. So we've made an alpha keto acid. And at the same time, we also have, from the perspective of the blue carboxylate, we now have a beta keto acid. So we've checked off both of the requirements for decarboxylation. What happens at this stage is, and we'll push the arrows for this a little bit later, but I'll give you a preview. Lone pair electrons on the blue carbonyl carbon kick down to form a pi bond, which makes CO2. At the same time, we're going to break the bond between blue carbonyl carbon and alpha carbon, and electrons are going to go on the alpha carbon, basically. It's and alternatively, you could imagine the electrons coming over here and then going onto this oxygen to make the other resonance structure of the enolate. The beta keto group creates a place for the electrons to go once CO2 leaves. So the reaction we just talked about is using NAD plus to oxidize an alcohol to a ketone, and then decarboxylation of the resulting beta keto acid with loss of CO2, which is these atoms there. Yes?
Did you say that beta carbon was the same for both?
No, I said that the ketone is beta to the blue carbonyl carbon, but alpha to the orange one. And that when we want to do decarboxylation, we know how to do that with either a beta keto acid or an alpha keto acid. In this molecule, we have both functional groups. So there's our first CO2 gone. And we also generated a molecule of NADH, so that's happy. That's a payoff molecule. Notice that we started with something that was 6 carbons, but we lost one, so now we're down to 5 carbons. This is called alpha ketoglutarate. We still have our 2 carbons from acetyl-CoA in our molecule. Alpha ketoglutarate is an alpha keto acid, and we can lose CO2 from this alpha keto acid. This is the bond between the carbonyl carbon and the alpha carbon that's going to get broken. We can do that with what's called the alpha ketoglutarate dehydrogenase complex, and it works just like the pyruvate dehydrogenase complex. So you've seen that before. We'll go through it again so that you can appreciate it again, but the chemistry is exactly the same. We add TPP to the ketone carbon to create a place for the electrons to go. Then decarboxylation happens. Then we attack the disulfide. Then we get thioester exchange, and so on. And then NAD plus is used to reestablish the disulfide. So though this looks unfamiliar to it, you have seen every step in this mechanism before. We lose the carbons here as CO2, and in its place comes coenzyme A, and our product is a thioester. So we have now accomplished our original goal, which is let's lose 2 molecules of CO2. Now, if you're following along, this is fascinating. We've lost 2 molecules of CO2, but none of those carbons were from acetyl-CoA. The asterisks still indicate the original carbons from acetyl-CoA. So they're now embedded in this 4-carbon molecule. Where did the others come from that we lost? Well, they were in oxaloacetate to begin with. All right. Questions getting to there? That's sort of the first, it's probably more than half of the citric acid cycle, but that's the first major goal accomplishment. Yeah?
Was oxaloacetate, is that a product of the glycolysis system, or is that something, an enzyme?
So where did we get oxaloacetate from? The course of the citric acid cycle is one eternal round. We're actually going to make oxaloacetate in the remaining steps. Yep. So it was just there. Well, who put it there? It's always been there going around. Yep. What else? Yeah.
You said that with the beta keto carboxylate and the alpha keto acid, is like both of them happen, or both of them can work, but is one preferable?
Yes, so it's a good question. Both beta keto, and when I'm using acid and carboxylate sort of interchangeably here, though if we want to be technically precise, these carboxylic acids always exist in their carboxylate form at physiological pH, so I guess I should be a little bit, it's just acid is easier to say than carboxylate, so I apologize for that. Decarboxylation of a beta keto acid happens spontaneously. Decarboxylation of an alpha keto acid, you have to have a big enzyme complex to make it happen. So that's why you decarboxylate the beta keto carboxylate first, and then you go on to the next one. Yep. Yes?
This is the intermediate of what?
So what's here is the intermediate of isocitrate dehydrogenase. So you start with isocitrate, it gets oxidized to oxaloacetate, but that doesn't stay around long. It immediately decarboxylates in the enzyme active site to make that. So some people will consider this a separate step in the citric acid cycle. It's not a different enzyme. It happens, you oxidize, and then it happens, boom, in the enzyme active site, and then that's the product. But it's important to see both things happen, because you can't anticipate that the decarboxylation is going to happen until you know that you oxidize that alcohol to the ketone. Okay, others? All right, let's overview the last little bit, and then we'll go back through and start pushing arrows. The product of the next reaction is called succinate. It's a 4-carbon diacid, and if you look at where you were, succinyl-CoA, a 4-carbon thioester acid, it looks like, oh, this is easy. All I have to do is hydrolyze the thioester. Nature could have water attack the carbonyl carbon, then kick off the thiol as a leaving group and get succinate. In fact, that's pretty much what we did up here to citryl-CoA. It turns out, though, that's not super efficient because thioesters are a level 1 reactive electrophile, and nature can use that. It's a high energy compound. Nature can use that energy to make other high energy molecules. In other words, nature isn't interested in wasting this thioester. So what happens in this next step is basically, first, we use phosphate dianion as a nucleophile. It attacks the thioester. What's the LUMO of the thioester again? Pi star, right? Carbon, oxygen, pi star. So you're going to see in the first step of this reaction that lone pairs on the phosphate attack the carbonyl carbon. You break the pi bond to get an intermediate, which kicks down, and then the thiol leaving group leaves. You make an intermediate acyl phosphate, and then from that acyl phosphate you make GTP. So we'll go back and look at the mechanism, but basically you go from thioester to acyl phosphate to phosphoanhydride in GTP. And in some ways it's not so very different from the phosphoglycerate kinase step in glycolysis, where you take 1,3-bisphosphoglycerate and ADP comes in as a nucleophile. Okay, so there we generate a GTP. We've already generated a couple of NADHs. Last couple of steps, succinate. If you compare succinate to oxaloacetate, both have 4 carbons, but oxaloacetate has a ketone that's alpha to one of the carboxylates. So we need to oxidize this CH2 group to get it to be at the level of ketone. So there's 2 steps. One of these is catalyzed by something called succinate dehydrogenase, and it basically, a base basically removes one of these protons, electrons kick down, and hydride is delivered to FAD. And I'll show you how that happens a little bit later. That generates fumarate, which is another example of an alpha beta unsaturated carbonyl compound. And as we've talked about above in the isocitrate step, alpha beta unsaturated carbonyl compounds are electrophiles at the beta carbon. And of course, this one is alpha beta unsaturated in 2 different directions, and the beta carbon being electrophilic. So we're going to see water act as a nucleophile, attack the beta carbon, and then protonate on the alpha carbon. That's going to give you this product malate, where the OH from water is now attached to what was the pink beta carbon. And once you're at malate, it's really easy from that point on. All you have to do is NAD plus mediated oxidation of a secondary alcohol to kick off hydride as a leaving group. Hydride gets delivered to NAD plus, and then you're back to oxaloacetate, and you're ready for another turn of the citric acid cycle. Yeah?
Where did those 2 carbons go?
What 2 carbons?
The ones that were marked as the
Oh, great, yeah, thank you. So the 2 carbons that were marked as the original, up through succinyl-CoA, we can still tell where they are. Once you get to succinate, notice that I could star them, but notice that this carbon is identical by symmetry to that one. Maybe I'll redraw the molecule again just so that you can see it. When 2 atoms are identical by symmetry, they are indistinguishable and you lose track of them.
so it's a little bit
From that point on, we don't know which is which. You would estimate that in about half of the molecules it's these two, and about half it's these two, but they're identical, so you can't tell at that point. So we totally lose track. From now on, though, the next time we go through, you need to think, okay, any of these 4 carbons in oxaloacetate could be from acetyl-CoA. And so the next time through, those are going to be the ones that come off. Yeah, and I've tried to, this is the longest I've ever tried to follow carbons through. You totally lose track of them at this point, and it's sort of pointless to look. One way you could do this, though, and people I think originally working this out did this, is you can make molecules of acetyl-CoA where the carbons are radio-labeled, meaning they have 1 extra or 2 extra neutrons, like C13 or C14, and you can track those. And so the experiment you would do is you'd start with C13 or C14 labeled acetyl-CoA, and then you just look at each of the intermediates along the way and say, where are my labels? And you'd see, you'd predict based on succinate that the labels should be in all of the places. Yeah. You could probably follow it through as a function of time, though, and see how long it takes them to get incorporated. I don't know if anybody's done that, but yeah. What else?
How do you know which one's beta carbon and alpha beta carbon again?
Sorry, how do you know which one is?
How do you know which one to label carbon and beta carbon?
Yeah, so with our labeling alpha and beta, those are relative terms. They're always relative to a reference point. So you got to pick a reference point, usually the carbonyl carbon, and start counting from there. In some places, like I think you asked earlier, you could ask, in oxalosuccinate, is this one a beta carbon too? Sure, it is, but it doesn't have a ketone on it. This one does, and that's the functional group we're looking for.
So beta carbons always have to land on a ketone?
No. Beta carbons are just 2 away from the carbonyl carbon.
So if you're looking back down to the L-malate,
Yes.
could you technically also label the other carbonyl carbon and then alpha beta having beta just beta carbons?
Bingo. Yep. It's all relative to what. Generally, we focus on functional groups that are important in how we describe things, but you're absolutely right that the pink beta carbon is alpha to the blue carbonyl carbon.
So then what's the importance of, in this case, having the OH group with beta instead of
Well, the point was when I show you the mechanism for how this happens, basically a nucleophile, water is going to act as the nucleophile, and it's going to attack the beta carbon and move electrons onto the alpha carbon where they're stabilized by resonance. So you have to attack from the beta carbon so the electrons can be on the alpha carbon, stabilized by resonance with this carbon-oxygen pi bond.
So beta carbon's always the one getting attacked.
Yeah.
Instead of alpha.
Yeah. Yeah.
In this case, though, you could attack either because they're both alpha.
In this case, because it's identical, one's beta to one and the other's beta to the other, so you could attack either one. And you must presume that either one does get attacked, though you always end up with that stereochemistry. The enzyme controls that. Yeah?
Going back to the succinate molecule, why is it, remind me again why the H attacks the FAD and not the FAD attacks the H?
So arrows always start with electrons. FAD, I haven't shown you how this happens, but FAD is a H minus, a hydride, meaning hydrogen with 2 electrons, acceptor.
It's kind of the same as NAD.
Kind of like NAD+, yep. So this is just to indicate that this hydrogen with its electrons is going to end up in FAD. We'll show you that mechanism. That'll probably be next time, though. All right, others? So that's your overview. You're going to want to know the intermediates. You're going to want to know the starting materials and products of each reaction, what they're called. You want to know the names of each enzyme. And then we're going to work on arrow pushing. And Again, if you approach this with just, oh, I need to memorize it, it's going to be really hard. If you add something to that, if you add chemical intuition and what's nature trying to do, and then everything we've learned so far about protonation, deprotonation reactions, addition, elimination reactions, together with the level 1 to level 4 electrophiles, and try to work your way through it from that perspective, it'll be more doable. I think that's a good place to pause. When we come back after the break, we will dig into the first part and just get as far as we can go with the arrow pushing.